I'm going to talk about some performance parameters in this video, starting with the CPU clock time. So the clock period is the duration of one clock cycle. It's going to control how long it takes to run a program. A program consists of instructions, and each instruction takes one or more clock cycles to run. So the clock period is going to determine how long it takes to run a program, and it's expressed in seconds. And the frequency is the inverse, and it's expressed in hertz or seconds to the -1. So the frequency would be the inverse of the clock period, so in this case it's 1 over 250 times 10 to the -9. The amount of time it takes to run a program is going to be this clock cycle time, like we just discussed, times the number of cycles in that program. And it can also be expressed as the number of cycles to run a program, which would be the number of instructions, and the number of clock cycles per instruction, which we'll talk about in the next slide, divided by the clock rate. So if you want to improve performance, and performance is defined by how long it takes to run a program, you want to reduce the number of clock cycles, or you want to have a faster clock. Okay, we're going to go over an example problem. We have a computer that can run a program in 10 seconds, and it has a 2 gigahertz clock rate. We like to run that program in 6 seconds. We found a faster clock that can do it, but it causes 20% more cycles. What's the speed of our new clock? So first we're going to get the number of cycles in our program. That's going to be the time to run the whole program times the number of cycles per second. So this will give us seconds per program times cycles per second. So this is going to give us the number of cycles in the program is 20 times 10 to the 9th. To get our new clock speed, we take the number of cycles in the new program, so that's 1.2 times our old number of cycles, and we divide it by the number of seconds to run the whole program. So that would be cycles in the program divided by seconds in the program, which will be units of cycles per second, and that's 4 gigahertz. So we've got a clock that's twice as fast. Another performance measure is the clock cycles per instruction. So each instruction that's run will take one or more clock cycles, depending on how complicated the instruction is, and we would like to get a count of the clock cycles per instruction for a program. And then we can express the number of clock cycles by the number of instructions in the program times the clock cycles per instruction. And the time to run a program is the number of instructions times the CPI times the clock cycle time. So how many instructions a program takes will be determined by not only the program, but the instruction set architecture and what compiler we're using. Here's an example of calculating CPI. We have a computer that has a cycle time of 250 picoseconds and a CPI of 2, and a second one with 500 picoseconds and a CPI of 1.2. So which one is faster? We get fast by how long it takes to run the program, which would be the instruction count, times the CPI, times the cycle time. So for this one, it would be I times 500. For B, instruction count times CPI times cycle time is I times 1.2 times 500. So that's I times 600. So A is faster. So to think about this, to get CPU time, it's going to be instructions per program times cycles per instruction times seconds per cycle. So we cross out the cycles and the instructions. So we get seconds per program. So if we have programs with a number of different instruction classes, some more complicated than others, we calculate the total clock cycles in the program by multiplying the instruction count for individual instruction types by its CPI and adding them up. Then we can get a weighted average of CPI by dividing those clock cycles by the total instruction count. So this gives an indication of how complicated the instructions in this program are. Again, the CPU time to run a program is the number of instructions in the program times the clock cycles per instruction times the clock speed. So if we want to improve performance, we need to decrease the number of instructions in the program, or decrease the CPI, or decrease the speed. So changing the programming language or compiler can affect the number of instructions in the program and the CPI. What algorithm we're using will affect those things. That's not really hardware dependent. If we have an algorithm to run, we have an algorithm to run. But hardware dependent is more the programming and the compiler. The instruction set architecture can also affect this. So if we want improvement, we can look at using a different computer with a different ISA or a different programming language. Another performance measure is MIPS. So MIPS is the instruction count divided by the execution time times 10 to the 6th, or the clock rate divided by the CPI times 10 to the 6th. It's easy to think about, but we have to keep in mind that to compare two values of MIPS, the computers have to be using the same instruction set architecture, and really they should be running the same program, because differences in programs can cause different average CPI. So just be careful with MIPS. An example, I'm doing problem 1.7 on page 56 of your book. So assume that for a program, compiler A results in a dynamic instruction count of 1 times 10 to the 9th instructions per program and a time of 1.1 seconds, while compiler B results in a dynamic instruction count of 1.2 times 10 to the 9th instructions per program and an execution time of 1.5 seconds. So what's the CPI for each program, given that the processor has a clock cycle time of 1 nanosecond? So the CPI is the cycles per instruction, and that's going to be cycles per second times seconds per program times the inverse of the instruction count. So that's CPI of A would be the inverse of the cycle time times 1.1 times the inverse of the instruction count. That's 1.1. For B, inverse of the cycle time times the time to run the program times the inverse of the instruction count, which is 1.25. Part B, assume the compiled programs run on two different processors. If the execution time on the two processors is the same, how much faster is the clock of the processor running compiler A's code versus the clock of the computer running compiler B's? So the cycle time of A over the cycle time of B is how much faster A is than B. So the time to run a program is seconds per program, which is seconds per cycle, times cycles per instruction, times instructions per program. So we have TB times CPI of B times instruction count of B equals cycle time of A times the CPI of A times the instruction count of A. So TB over TA equals CPI of A times instruction count of A, CPI of B times instruction count of B, and that is 1.1 times 1 times 10 to the 9th divided by 1.25 times 1.2 times 10 to the 9th. That's 0.73. So B is actually faster than A. Part C. A new compiler is developed that uses only 6 times 10 to the 8th instructions. So this is our new instruction count for compiler computer C. And has an average CPI of 1.1. So that's pretty amazing improvement. Not only did it reduce the CPI, or use the lower CPI than one of the computers, but it also reduced the instruction count. So that's an amazing improvement. What is the speed up of using the new compiler versus using compiler A or B? So we want to know what's TA over TC and what's TB over TC. So we have to have TC, which is going to be seconds per program. That's going to be seconds per cycle times cycles per instruction times instructions per program. So TC is going to be 1 times 10 to the minus 9th. We're using the same processor, so it has the same clock speed. Cycles per instruction is 1.1, and the instructions per program is 6 times 10 to the 8th. So that's going to be 0.66 seconds. So TA over TC is 1.1 over 0.66, and TB over TC is 1.25, or no, 1.5, sorry, over 0.66.